so I've been interested in networks for ages, and one of the things that sort of often draws people into networks immediately are these visualizations. And there's, on the one hand, they're kind of like just sparkly little like things on the side that sort of make us think, ooh, isn't that pretty? On the other hand, one of the problems with understanding networks are that there's these high dimensional features. There's lots of information in them, and any good index is only going to capture a little part of that. So one dimension, such as centralization or the degree or something like that. Whereas the picture gives you sort of a gestalt of it. It gives you sort of a better overview of what's there, if it works. And so the key is to find a strategy to visualize these networks that provides information without providing a lot of bias at the same time. And so I want to go through a few things that have to do with networks and visualizations. I want to give a little history, let you see what's sort of been done in the past. Talk about like why we might do this at all, and then go through most of the times when we spent on what are these kind of strategies that we can use to make a visualization more or less effective. So the very first network study started with Wheeler's work about this classic mathematical problem known as the bridges of Knigsberg problem. And the thought is it's a city of bridges, and then there are these islands. There's this island in the middle of the river. Excuse me. And it's a nice little puzzle. Could you imagine walking over one bridge and over a next and cross every bridge only once and never twice? Right? This is the way the problem is set up. And if you could imagine thinking about this just theoretically, if you just have bridges on a straight line, this is not a problem, right? You go up, down, up, down, up, down, up, down, and there you have it, right? But if you have a network that looks like this, or a geography that looks like this, it's not entirely clear that you can cross one, cross the other, cross this one, cross that one, and not have to cross them all at the same time, right? And so what Wheeler did is he turned this into a graph. And this is the start of graph theory in mathematics. This is where it first showed its head. And it also raises this idea of abstracting from something that's real, like a point of land or a bridge, and turning that into this notion of points and lines. And so the idea of points of lines, or vertices and edges, had its start a long, long time ago. And this is where we sort of get our work. Network visualizations had their start probably in kinship diagrams. And this is where people saw them most likely or were most originally familiar with them. And so from classic cultural anthropology, you have the extent of descent from great-great-great-grandfather and so forth, down to cousins and uncles and so forth, or bureaucracies. And so this is an organizational chart for a bureaucracy in Russia in the early 20s. It looks a little like Duke today, but actually, I've asked the administrators every year since I've been here for a copy of the organizational chart, and they won't give me one. I'm afraid that they really don't want the answer. But for social network research, the original visualizations that really sparked everyone's interest were coming from Jacob Moreno. And what Jacob did is he focused on this idea of making the invisible visible. And so he had multi-relational color diagrams in his work in 1934. And he had a very rigid system for how he would draw his network. So gender was encoded in, females were in circles, males were in triangles. If it was a negative tie, it was in black. If it was a positive tie, it was in red, which we might do the opposite now. Just kind of an interesting difference in that. If the tie is reciprocated, he put a little cross line in it like this. And so in this case, there's a negative tie from MF to AC, but a positive tie from AC to MF. So they disagree on whether they are getting along, right? And in this network, you can just look at it, and you can tell that CM over here is not liked by anybody, right? So all the girls in this little cabin, these were runaway kids in New York. Everyone in the cabin seems to dislike CM, and even the people she's close friends with are friends with an enemy, right? And so if you want to figure out why CM might not be thriving in this environment, you might want to start here, right? This is at least a place to keep in mind. And this is the image I showed you the very first day, right? He exploded this idea. Each one of these little pieces is actually a cabin on this entire campus, and this entire graph is one giant colored piece. And the thought was you could look at it and sort of draw some inferences. And when your networks are small, right, and you can actually just look at them all, you can actually see, well, this is the kind of person that we might want to focus on, see what's going on there. figure out who's the likes most popular, who's the dislike most popular, what kind of people are have high reciprocity, and what forth. You can just look at it. It's just easy enough to expand by looking in your eyeballs. As they get larger, it's a little harder. Over the years, these ideas were taken up by a lot of folks, particularly in community studies. And so in community studies and agriculture, this is a beautiful series of books by Lundberg and Steele. And these are, each circle in these cases are a household, and they're sized by the SES of that household, so whether this was a rich household or a poor household. And so this was the richest household in the village, and everyone liked this person, right? So everyone reported who they're going to. What's amazing about this diagram, again, these were all done by hand in the 30s, is that if you actually go from page to page, they're very rigorous about the number of lines that go out of one page and come back into another, right? So in theory, a person could go through and reconstruct this entire edge list by going over to the maps that cross over to the other side. And so the amount of detail that people put into thinking about these very carefully, all again done by hand without any software to help them, was pretty remarkable. There's a tendency, once you have these relationships, you think, no, I have a map, I want to add a layer to it. And this is probably a basic theme of network visualization over the years, which is that we keep adding different amounts of information on top of the edges. And so in this case, again, we have households are the unit of analysis, but we have the proportion of which you visit one person who's either from your neighborhood or from a different neighborhood as a pie chart on top of the nodes. Size is based on the number of nodes you receive, and then this layering of some attribute, a color or a distribution or something like that on top. Remarkably, adding pie charts to a network was still really not an easy thing to do. There's only a handful of people who've written their own software to do it. It should be a trivial, but it's not done that often. Up until this point, up until the 50s, this is Nothaway's, what he calls a target sociogram. Up until this point, most of these kinds of layouts were really just done artistically. People would try to put things in a way that might minimize edge crossings or otherwise have a way to sort of make some sense where it's all laid out flat. But there's no guiding theoretical principle to figure out why one node would be in one place versus another place. It's just wherever the artist decided to stick it down on the page, and how much patience they had for redrafting these and drawing them by hand. And what Nothaway came up with was this idea of a target. And they thought was that there's people in the middle who are really important, and so we're going to put them at the center of the target, and people who are peripheral to the set, and we'll put them on the edge. And so we come up with some measure of center to edge, which then we ultimately end up calling centrality. Right? And in his case, he split up the vertical side from females on one side and males on the other. Now, circles and squares are kind of boring, so you could imagine making them boys with bow ties or bows in their hair, right? And at this point, you actually had an algorithm that lets you figure out the layout, which was a pegboard with rubber bands, right? So this was literally the way you could do it, and you get a draft of it by moving this around. Rumor has it, I haven't seen it, but rumor has it that there's a 3D version of this where they took a series of a bunch of an abacus, right? I don't know what a collection of abacus would be, but abaci, right? So take a bunch of them, and then you can run edges in all three dimensions. Seems like a lot of work to me. But you can still do target sociograms. This is using PAEC. There's a circular layout where you can restrict nodes to being on each of these points and move them around by hand if that's what floats your boat. The idea of having a dimensionality to the network, right, that there's some meaning from edge to the center, people then immediately took that idea and started adding dimensionality to the axes and the kinds of graphs we're used to looking at. And so in this case, there's an SES meaning to the vertical axis, and then the groups are aligned according to the x-axis in a way that tries to make sense of it. This fails miserably, right? This is just not a particularly good use. And what happens is I think people start going down the wrong path historically. They start moving down trying to layer more information or fix meaning of edges as opposed to thinking carefully about what sort of networks might be good in themselves to do. So one solution is if it doesn't work in 2 dimensions, let's use polar dimensions. Those tend not to work particularly well. Let's embed it on a hypercube. If you get a really, really big network, that's also hard to see. This turns up, this is an internet. This is a map of computers connected to each other on the internet. So you can see that. Over time, of course, it moves from these scientific strategies to what I would say is a little bit more silly strategies. So these become some popular for marketers. This is an advertisement about how it's trying to sell hand cream, and the idea is you start with one person, she tells her friends, and so forth. You see some little funny things like that. Not sure it's scientifically all that interesting, but maybe it sells some ideas. Journalists then pick it up and start doing things that are even worse layouts. Here you're trying to layer on different. This is a New York Times thing about people business people where they went to law school and who they worked with at various and sundry times. You could imagine looking at scandals, right? So the New York Times does this all the time. They're sort of the leaders of the infographics. This is my world's favorite worst network diagram, in part because it's so damn important at the same time of being so bad. What you have here this is a real model of what they thought was going on in Iraq at the time, right? And if you want to take it to say that what this really means is that it's a complicated mess there, then yes, it's a complicated mess. But if you really thought you could learn anything from this, it's kind of remarkable. Sometimes people just make jokes out of them, right? So this is a spoof of the Christakis and Fowler papers, that your networks make you fat. And I actually think this is a remarkable image because these are real points and lines connected here. So I have no idea how someone actually got this to work, but it's pretty remarkable. Unless we think, of course, that only journalists make bad network diagrams. This is a published diagram in a network, and I think that if you think you could learn anything from this showing up on a printed page somewhere, you're fooling yourself. And so the question is, well, how do we get from something like this to something that's scientifically useful and hopefully aesthetically pleasing at the same time? And I think that we have to sort of try to walk through boundaries between science, art, and craft to make this happen. And so if the goal from Moreno's is to make these powerful invisible structures visible, how do we do it in a way that we can actually see it? And the intuition that Moreno gave us was that network science could be something like a telescope, right? We could sort of look out at the world and see it in the same way that we might see planets moving around another place. But of course, the problem is if you're not really careful what you're looking at, right, our eyes can be deceiving. And so we really want to have some way to draw these diagrams where we're seeing what we're communicating, what we want to be communicating as we're working. And so, what distinguishes a scientifically effective visualization? There's a couple of dimensions I'm going to move through here. First is a basic visualization craft, sort of a style or rhetoric. This is what's coming out of Tufte, out of some of the visualization textbooks. I'm not going to spend a lot of time talking about these features because these are general to all types of data visualization. We'll touch on them a little bit, but by and large, things like clarity, scaling, coloring, layering information, these kinds of things, these are common across any kind of scientific visualization, and I want to focus on the things that are unique to network visualization. But these are going to pop up, and the distinction between a good coloring and a bad coloring can mean the world of difference when you're sort of trying to make sense of something. But we're not going to spend a lot of time talking about it. That distinction between craft and not, I think ultimately has to do with revision and care in trying to really craft a visualization. So these are two images of the exact same network. On your left is what comes out by default without anything else from a screenshot from PAYAC, right? And as that comes out, there's not much to it. You can't see much distinction. We take the exact same network, do a little movement around on the edges, color by centrality, size by degree, put a nice scale on it, change the size of the nodes and the density of the lines and the thicknesses and so forth, and it's just a lot easier to look at, right? And I want to talk about how you get from this to that. That's really the goal today. Questions, comments, thoughts thus far? All right, so the key element I think that networks provide for us, at least in one sense, is a way to represent social space. So if we want to represent social space, the question is which social space do we want to represent? The idea here is that it might be a social space, but it's probably not a perfectly accurate social space, right? The problem with networks, one problem with networks the space analogy with networks, is that most spatial things we can see are 2 dimensions, maybe 3 dimensions, but networks can be n-1 dimensions, right? So there's a huge amount of a dimensionality of these networks, so we are forced to distort them in some way. And so the question is, can we distort them so we can see it in a way that doesn't fundamentally change the story we want to tell? And so you can see here, this is a two-dimensional representation of a network. This is a three-dimensional representation of the network. It turns out that 3 dimensions are really, 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 really hard to see on print. If you can't move it around or play with it, what you get is occlusion. You get nodes that are stuck behind other nodes. And so a 3-dimensional representation, we all sort of think, well, instead of distorting it, I'll just add a 3rd dimension. And it does create better fit. It makes it so that you essentially don't have to distort it as much, but it's often much, much harder to actually look at.
Hey, Jim.
Yeah.
A while back, don't flip back, but you showed a picture of a visualization of, that's very common. It looks like fiber optics around some kind of Christmas bulb or something. So the goal there does seem to be 3 dimensions. You see these everywhere, right?
Yeah.
And you quickly toss to the side, except you do see them everywhere. And I've been wondering now, and I guess previously, why that is. Is it that they're trying to capture 3 dimensions?
Yeah, so in that case, it's even...
It falls flat because of the coloring?
Yeah, it's... so you're going to see 2 versions of that. But the image I showed before was actually even worse than you might think. It's not only the 3 dimensions, but it's 3 dimensions on what's known as a hypersphere. And so if you can imagine a fisheye lens in 3 dimensions, it's squishing things off to the side. And what the software she designed is to actually allow you to go in and manipulate it, so you can twist things around and move. But if you just try to present it as an image to look at, it's exceedingly difficult to make sense of.
And that's why everything was
there
was basically,
right.
right.
Exactly, and that's exactly what's going on there. All right. I don't know what time to talk about that. Let's skip that idea. So I think that, so what distinguishes a scientifically effective visualization? I think we have to think about the different kinds of network-specific graphic problems. And it's ultimately going to be the case that once you have a network problem you're trying to explain, a visualization will become relevant to you that might be good for describing, say, edge-level features that won't be good for describing dynamics. And so because networks have so many dimensions to them, you often have to pick what it is you're trying to show. And it turns out that this creates a tension between these 3 pieces. Right? So on the one hand, as scientists, we're fundamentally interested in data fidelity. We don't want to lie with our pictures. On the other hand, we want to answer a real question in a way that has a pleasing visual strategy. And these things don't always line up quite nicely. So we have to think about how we might do that. All right. So what are the elements of a good visualization? I think for a good scientific visualization, it has to build some intuition about the social process that's generating the network. So you want to have some idea about the network should tell you a story that's obvious for what's going on in the setting. The example Jeff gave a moment ago that showed us that the network was highly clustered by grade, we can tell a nice story about that. It makes sense. The kids spend a lot of time in the same grade as their peers, and so the clustering by grade is intuitive when we see it colored up there. You need to, I think, a good visualization succinctly captures the high-dimensional properties of a network. Right? If our goal were just to figure out who has higher degree or lower degree, I'll just count the number of edges. I don't need a visualization for that. I have a really good single-dimensional measure. What networks provide us is a multi-dimensional measure simultaneously, or images, excuse me, is a multi-dimensional representation that should complement the single-dimensional measures the metrics we're going to calculate directly. It should be worth the space, right? So a picture really should be worth 1,000 words. If it takes me more words to describe what's going on in the picture than it does for you to see it, then it's not worth the effort. If it's a giant hairball that just looks like a hairball, then it's not worth the effort, right? If you can't learn anything from it, then don't waste the space. And finally, I do think that they should be pretty, right? There should be something about them that you go, yeah, that's nice, right? It shouldn't be jarring. The colors shouldn't be the kind of thing that hurt us. On the science side, science can hurt. I mean, colors can hurt. As much as I love Payek, like they have no color sense at all, right? So anyway, those are what I would consider sort of aesthetic features to some degree, or communication features. As scientists, we have another layer, right, that we want to think about, and that is that we often want to be able to replicate our results, right? So if it's not good if I do a visualization and you do a visualization the next day and they're radically different, then that somehow seems wrong, right? As a scientist, we'd like to be able to have our work be consistent and replicatable. There's a quantification feature. We'd like to know whether or not these images fit, right? We'd like a goodness of fit of some sort to see is this a good measure or a bad measure. And again, there should be some theoretical relevance to why this is to what we're describing. I like to use an example for why we visualize networks that comes from Tufte, and it's been around for a long time. It has to do with scatter plots, and some of you may have seen this. But imagine that you have these three series, and you do a bivariate regression between x and y. If you take these three series and do a bivariate regression of x to y, you're going to get the exact same summary statistic up until things even like the sum of squares across all three of these pieces. All right, so from a basic regression standpoint, y1, y2, and y3 are exactly the same. Right? But if you look at them in a scatter plot, this is y1, this is y2, this is y3. Right? We see something fundamentally different across these three that are missed in the statistical summary. And this is what the power of visualization is. It lets us see something about the whole, right, as opposed to a single collection of the individual pieces. Right? And so what I would like to do is figure out, is there an analog to this for a sociogram? So if we want to think about a network, can we move from a series of statistics that have today, say, our ergon coefficients, can we complement those with something like a visualization or scatter plot that would make more sense of the underlying coefficients we're seeing? Well, if you want to do that, you can ask yourself, what makes a scatter plot work? Right? A scatter plot's pretty easy. Each point represents a pair of numbers. So this is 4 and 3. This is 7 and 8. But this picture is the exact same data. Right? So this is a perfect representation of the data table. Right? I've just randomly sorted the x-axis. Right? Now, don't know why I would do it, right? That seems like a silly thing to do, right? But if I want to recover the data from this image, right, I can come here and say I got 4 to 3, I got 6 to 6, right? This is a perfect representation of the data, but somehow this is more informative. And the reason it's more informative is if we understand the ordinality of the axis, right? We've been trained, we have a convention. And that convention is that you don't randomly sort axes on a scatter plot, right? You run them from low to high, right? And if you didn't do that, it doesn't make any sense. And you realize what that allows you to do intuitively is you're not just looking at the 9 points that are on this plot. You're looking at the 9 squared relationships among all of those points, right? I'm comparing this piece to that piece and realizing that they're distant in this dimension and distant in that dimension. And so I get all of these distances simultaneously. And you don't get that if you just get some sort of a random arrangement of the pieces. And so what that's telling us is that there's an underlying space, and that space is meaningful. And we want to do the same thing with networks. We want to think about the kind of space that's underlying the graph so that we can draw it nicely. Unfortunately, the current state of affairs in network visualizations is far from that. These are 3 representations of the exact same data that have showed up in print. This is the Zachary Karate Club that Peter Muka showed us yesterday. You have the image, I think this is the actual image that Peter showed us yesterday, but you've seen it in lots of different formats. Again, this is no different than taking a scatter plot and randomly sorting the edges. Right? What we'd like to be able to do is have the same thing every time. The other sort of insight we can gain from scatter plots is it's really easy to layer on lots of different information and make it possible for people to get more from the scatter plot than just the association between x and y. And this is an example that's coming out of Gapminder. If you haven't ever gone and played with Gapminder, it's a wonderful exploratory analysis tool because you can color things by country. This is a country-level data set. You can color them by lots of different variables simultaneously to layer on multiple dimensions. So you get the primary dimensions between x and y. You get a 3rd dimension in color, a 4th dimension in size. You can get a 5th dimension in movement over time as you move the Gapminder through. It's a very nice way of thinking about layers and layers and layers of multiple information on the same figure. So the problem summary then is that the benefit to network graphics is that it's supposed to make network visible, make visible the invisible, right? We want to get a sense of reality to unobserved features. We want to make them pretty and communicate. It also provides a multidimensional insight to get to some processing, and it helps us think by organizing, arranging, or abstracting features that are really important, at least the part that we want to communicate. The challenges are that there's no consistent or obvious display frame. There's usually too much information, so we have to throw some things away. We have to deny the data in Eric Leifer's old terms. And we have to find some kind of a scale. It turns out that it's a lot easier to display small networks than it is large networks. And it might be the case on large networks that we want to do something different than we've done on the other side. Most of us are also a little bit impatient, right? So if you can imagine a perfect layout, if it takes a month to run, we're not going to do it, right? It should be some set on that front. And so each of these kinds of problems then have given rise to a set of heuristics that computer programmers have built into network visualization software to try to highlight one element or another. So for example, we might want to have consistent edge lengths, that if I'm one step from you, I should be one length from you. So a step should equal a length. And so that might be, I might have a layout algorithm that really prioritizes consistent edge lengths, but that's going to lead to lots of line crossings. So another thing that makes an image nice so I can trace paths around are to avoid line crossing. And all of these things play on simultaneously. And what this means is that as a programmer, if I sort of favor one of these over the other, I'll get a different kind of a layout. And this is why the computer programs that we give can give us radically different images for each one for the same data. So this is from a program called YED, Y-E-D. And there are a dozen different default layout programs in that software. And each of these, in some sense, tell the same story, but because it's the same data. But again, depending on the underlying rule that's guiding it, you wouldn't be able to tell that this network is necessarily the same, say, as this one. All right, so that's set up the problem a lot. Now I want to spend a little more time talking about the other pieces. So I think there are essentially two basic types of broad categories of network layouts. The first is some layout where there's a realistic dimensionality to the y-axis. The other is that there's not, where the fundamental issue is a spatial distribution, more like a map as opposed to like a data infographic. When you have a meaningful y-axis like hierarchy, then you like to be able to highlight that because readers can see that there's a flow from one side to the other. And so if there is some dominant organizing feature in your network that can order nodes from a source to a destination, then it makes a lot of sense to put that into the graph. And this is what Giovanni showed us a minute ago when we looked at these trees of RDS seeds. So we start with one node, they recruit somebody else, they recruit somewhere else. It's a natural hierarchical structure. It makes sense to display that as a hierarchy from top to bottom. The space-based layouts, the way they work is that they try to focus on proximity. And they're working on this notion that social space could be represented as a two-dimensional physical space. And to do that, you imagine that people that are close to each other are going to be within the same radius of each other. So there's a one-length radius around each of these 3 points. And that radius, if it remains the same everywhere, creates a consistent distance between points. The problem is, from this graph, I can tell that 2 points are near each other, but I have a really hard time figuring out where the root of the hierarchy is, right? So if your network has a strong hierarchy, this won't show it. On the other hand, if your network doesn't have any kind of hierarchy built into it, forcing one on it is a really bad idea, right? So in this case, the algorithm's going to do its best to take nodes that have more outgoing ties than ingoing ties and put it at the top, but it's never going to fit well, and it's going to look like a jumbled mess. On the other hand, because the pressure towards consistent edge length are pushing nodes next to each other, what you end up seeing here are clusters of nodes that are friends with each other will be drawn to a similar region of the space, and those that are not connected to each other will be pushed further out in the space. The cost that comes from this is there is no up, down, right, left, in or out, right? There's just proximity. This image fits exactly the same if I rotate it, if I twist it, if I flip it upside down, right? So within those kinds of spatial transformations, this network will be consistent, but I could easily run the model again and flip it over and get a different result, right? It wouldn't be different in terms of proximity, but it would look different than its first reaction. The final sort of direction of, there's another sort of version of thinking about networks, which is to think about a fixed coordinate layout. In this case, you have some other information that you're fixing the coordinates to that is not a network base. In the classic example, these are something like geography. So if I have, in this case, each node is a hospital, and so hospitals actually have a real, like on the Earth, latitude and longitude, so I can place that on the map and I know where they are. And this is what the network model of that looks like, a space-based model of that looks like. Now, I think depending on your problem, right, well, this might be a better visualization than that, right? It turns out from a social space standpoint, this model fits better than this model. I'm going to explain what this fit statistic is here in a second. But the advantage of this is that readers know what the map of the United States looks like. Right? The problem is I have no way to figure out what's going on up here in this little purple cluster because there's too many people around Boston, whereas the Midwest and the West takes up the entire size of the space, even though there aren't that many hospitals out there, right? So physical geographic maps fundamentally conflate population density with spatial arrangement. If that's okay, if that helps you communicate your piece, that's fine. And if my story is about how fast a disease can move from Texas to Seattle, then it's nice to have this moved up because I want my policy people to realize that they're at risk from things going on in Texas, which is really hard to explain over here. If instead I want to figure out essentially the differences between clusterings in one set or the other, then I might prefer this kind of a layout. All right, so the fit statistic that I'm fitting here on the bottom is literally the correlation between the geodesic distance in the network and the Euclidean distance on screen. And so if I manage to do this trick perfectly, right, where I have the distance on screen is equal to the distance in geodesic space, that correlation would be perfect. Right? And what I'm getting over here is the extent to which is a poor fit, the distance from 1 is really the number of nodes that I had to squish down on top of each other because there's too many dimensions. And so it turns out that a geographic representation of the nodes, right, is not quite as good a fit from a representation of the underlying social space as a four-space layout is, as this sort of edge-constrained distance sort of layout is. But it might communicate something different. John?
So I'm assuming Pyac gives me this as a nice little...
It does now, yes.
That's cool.
I talked Andre into adding it to the list, so it's there now. The fact that I've been using this program for longer than I care to remember, Andre answers my emails. So he usually puts in what I suggest. Sometimes it's good, sometimes it's not. Now there's another kind of fixed layout, which is actually something like a circular layout. And usually I find a simple circular layout where you take the entire network and put it in one big circle pretty useless. Right? It doesn't help us much. On the other hand, you can oftentimes do something that's a combination of these two, where I might take a network like this, right, where I have each of these nodes, and this is, I think, in fact, is the same network, these two graphs. And now I've laid it out in space, but there's a lot of mess here that I can't see, and I don't have a really sense of how many ties are in here because the nodes are on top of it. So I can leave those points where they are and add a circle on top of it. So a space, so here I've taken each cluster, and the arrangement between clusters is right at the macro level, and internal you can see that there's a high density internal to this one, a low density internal to that one, for example. So you can use these things in combination sometimes to gain some insights that you might not otherwise gain. And notice the fit on that one, 0.57, isn't that different than the fit over here, right? This is a network diagram you're going to see a lot out in the world. These are called chord diagrams, and so this tells you the flow, say from whatever this edge is. You follow the little arc arrow out over to this side. These are useless. All right? These are pretty. They're nice. This is the pie chart of network diagrams. All right. You should never use a pie chart in general sort of science and communication. You should never use a chord diagram. All right. They look beautiful. They are cool looking. Right. I'll grant you they have this sort of nice. But somehow I don't know what to get out of them. Right? It just doesn't seem that nice. Similarly, right? We've all, this is getting back to Lisa's point from earlier. We've all seen these kinds of diagrams, right? This is the Facebook diagrams of who's friends with who on Facebook, and what this tells you is that people live in cities distributed around the world. And more people live on the eastern seaboard than live in the Midwest, and no one lives in the middle of the Amazon who's on Facebook, right? That's fine, right? But this is what it tells us, and I think that we it's beautiful. Again, this is a wonderful, beautiful. And if I'm selling Facebook, right? If I'm out as a marketer, I want this on the cover of Time. But if I'm trying to actually do something scientific, it might be nice to know, in fact, that the parts of South Africa are actually closer to England than they are to other parts of Africa or something. And I can't tell that from this type of diagram.
Or that China exists.
Or that China exists, right, yes.
Well, do you have any sort of intuition about why these are so appealing? Is it
because they're sparkling.
they're sparkling?
Yes.
Yeah.
No, I mean,
Fiber optics,
in this case, it is literally that it's sparkling, right? I mean, it sort of looks like something that's bright and shiny, and so our primal urge is to be drawn to those things that are bright and shiny. So again, I think that it does depend on the question. This was a piece that we put. This is that same network where we really were trying to figure out the risk of one hospital to the other through the spread of patients. And so in that case, it was nice to be able to have the geographic spacing to it because it told us essentially how hard it was to get from Dallas to Boston or some such. But oftentimes, if you don't have a geographic question, then you might be better doing something else. Operations, network on a partition. I extract the subnetwork. I take the ones that have value. Control P. And now I have just the largest component. Notice the size went away. Why did the size go away? The size went away because I remember now without the isolates, my network is 69 nodes, but my size vector has 71 nodes in it. Right, so they don't match. So I have to either extract this subpartition or I have to recalculate a degree. That's faster. So this Control D gives me degree. Control Q draws by size. And so I'm back where I started. Now this is a pain in the ass. Right? There's no way about it, right? So this is a point and click, and you got to figure out how you're doing. You'll get used to it if you want to play with this much, and it's kind of fun. And it is, I think, one of the better layout programs for doing this. I often need to go in and move things around by hand, figure out what's there for that purposes. You can also do, we told this before, this the only 3D layout you have in PAYAC is the Fruchtman-Reingold 3D. So you go like that. It doesn't look that different at first until you hit the S, and then you can spin it around. Or the Z, and ooh, or the Y, go there, right? And so you can see things where things are if you want, and you can spin it around lots of different ways. And so, again, in this case, I've gone to 3 dimensions in this network. Does that actually improve my fit any? If I go to info, correlation, not much, right? So this is, again, pointing out that 2 dimensions do a pretty good job with a network this sparse of fitting where we are. The other layout options here are these MDS or the VOS layouts. MDS is multidimensional scaling, right? And so if you've done any of those kinds of things before, this is just a classic implementation of MDS. The nice thing is it's a random sampled MDS, so it works on really big networks if you want. So if I want to say, give me a 2D MDS, it says, well, how many nodes do you want to use? And if I could base this entire network, say, on 4 nodes that I'm going to do the MDS on, if I do that, it just randomly places the other around, and it's not a very good layout. Alternatively, I can say layout, MDS, 2D, let's use all 69 of them, go OK, and you get perhaps a somewhat better layout. I've never been particularly happy with the MDS layouts, but people like them because there's a model under the hood that works nicely for it. Right? Now imagine that what I want to do instead now is take this and identify clusters in the network. So a cluster, the communities in the network. I have that's a partition. It's a coloring of the nodes. So I'd come over here, identify communities, and there's the Louvain method. And so the Louvain method that Peter told us about is this one. I pick some options. I'm going to say the resolution parameter is just the default. Go ahead and let it run. And there I have it. And then I go back to Control Q again. So now I have clusters defined by the Louvain method. Let's lay it out with Kamada Kawai again. And so then we have these clusters. And you'll notice that this cluster has a node that's kind of on the edge over here. Maybe this node would have been better placed somewhere else. And this gives you a way to get in, look around, see whether or not these clusters are sensible, and do some of that kind of interactive evaluation of where things are at. It's a nice program for doing those kind of things because it is so fast. And just to give you a sense of that, if I were to I could best, took less than a second to run that one. If I were to do this on a network of 4,000, it might take 2 seconds to run. So it's nice and fast. Like, it's a really good, easy to use program. Now, what I pointed out before is that you might want to highlight the fact that I have clusters in this network, so you can do things like resize them, right? So I can say options, transform, resize cluster area. Let's make the clusters about half the size that they currently are. Right? Now my clusters look really distinct. Right? Now that's a lie. Right? That's not now the same layout algorithm that it used to be, but it might be useful for helping you think about what the communities are and making sense of them and making it clear to people. Sometimes I'll move nodes around if I need to, sort of highlight things such as that. If I then want to say it's too messy internal this layout to make sense of it, I can say layout circular using layout circular using the partition, and then it draws a circle within each of these partitions, right? And so that gives you a nice way of that. Now in this case, all these circles are way on top of each other, so I might do something like just shorten the edge, move them into each other, and resize them. All right. You can zoom in and out. Now you'll notice that the more resizing you do, sometimes you get the edges popping up on top in front of things. That's because of the z-axis sometimes gets some rounding error in it. So if I go options, stop that, options, transform, set the z-axis, and then go back to where they are. So these are the kinds of things you can do, and it's a really easy program to play with. It's a little easy to get lost in this program, so you start playing with different colorings, different sizes, and so forth, and you'll find yourself in different spots. And so that can be something of a pain in the neck. But otherwise, it's really a nice way to I'm going to go back to the Kamada Kawai layout again, just with Control K, and that puts me back to where I was before. It's a nice way to get these kinds of visualizations easy. Now, this visualization is pretty crappy, right? I would never publish this visualization because it's the default line thicknesses, it's the default colorings, all these sorts of things. And so what I would probably do instead is I'd export this to some format that I can then do some other. Once I get a layout or positioning that I like, and a relative sizing that I like, then I will often change colors and line thicknesses and these types of things in Illustrator or in your favorite SVD editing program or something like that. If I want to make it so it's linkable, like I said before, Control L gives me all my labels. And so now I have the node name, say, and I can say export 2D as an SVG. And then what it's going to do is it's going to export this to a program and give you that hover ability. So I can then hover over the nodes, and it won't print those node labels to the space, but it'll let me hover over it and have those things pop up as tooltips. Right, so this is what generated the images that Minaj is going to show you here in about 45 minutes to an hour or something like that. So this is I think that we're a little over time. We're getting close to time, so I don't want to go through all of the things this program can do. But it really is nice that way. You can do really big visualizations. You can do lots of things quickly, and it's fast. The biggest problem with it is that everything is relative to these objects. So here I have the network. Number 2 has 69 nodes. It doesn't know, right, that there's anything special about these. If I happen to have another network with 71 nodes in it, it'll work just fine, right? If I were to do something crazy like resort this matrix, it doesn't simultaneously resort this vector, right? So these things are just independent text files sitting on a drive somewhere. And so if you're not paying attention to what you're doing, it's really easy to you'll get something messed up that way. Jake, in the back.
Is there a help file somewhere for this, or like some kind of documentation tutorial?
Yeah, so there's a book called Exploratory Network Analysis with Payek. And it's by Cambridge University Press. That's the most thorough sort of description of everything. And I highly recommend it. It's a great little book. It walks you through each of these pieces. The online tutorial is miserable. What it is a single, it's just a data dump of every window menu option. So it starts with File, Open, and then works your way through. And so it gives you everything, but it doesn't tell you what to do with it. That's what the book will tell you what to do with it. And so it's a much better version from that standpoint. The other thing that's bad about this program is that it is, so I can shut the arrowheads off if I want to, so I can do all those sorts of options. I can say lines, I'm going to draw lines, graph only. So graph only gets rid of my arrowheads if I don't want them. I can convert arcs to edges. You can do these kinds of different sorts of manipulations if you want. If you have a really big network, let's see if I can get this really quick, create file network. So this is the PhD committee overlap network that I told you about before. Something that's kind of fun is you can search these networks nicely. So I can say control neighbors, and I can say Minaj. And let's see if we can find one or not. Do you have any students here, Minaj? Apparently not. So let's try Seth. All right, so there's a bunch of different Seths that turn out. So let's try Sanders. Yes, there's Seth. He's right there. I say OK. I say give me all everyone who's all the neighbors out to no limit. So I'm just going to walk all the way out. And go OK. I now have a complete neighbors of Seth Sanders in the network. I draw it by that. I can see that there's Seth in blue. All Seth's immediate neighbors in yellow. People 2 steps from Seth. People 3 steps from Seth, and so forth. I could, if I wanted to do, lay this out like this in Y direction. So there's Seth at the top of the world, sort of leading everything, and then everyone whose neighbor stuff sets moves down on the set. It's hard to see from the vertically, so I can say options, transform. Let's rotate this 2D, make it 90 degrees, right? And now I can see who are direct. These are the people that Seth has sat on PhD committees with in the last, I think right before 2005, for example. If I wanted to just look at the local neighborhood, I'd say Control E to extract. You would learn these things if you were going through it. We're not going to do it now. I could say it takes 0 to 2 to get the two-step neighborhood, draw the partition, and that's the local neighborhood of Seth Sanders. And I don't want to look at all of them per se, but Control D to give me the degree, and then Control Q gives me the different size. And so it's a nice way to explore really. This is why they call it an exploratory pool. You can move through these pieces, pull things out. It looks like he seems to have a penchant for hanging out with demographers, and there are a few people that are still in his network that are no longer here. Right. So this is the way these sort of programs work. All right, in the interest of time and moving forward a little bit, I want to do a quick just demonstration of some of the, just a quick like flash up of Gephi and then move on to the other side. Is that all right? So again, it's an entire program. It's fun to play with. It's free. And its real value is that it works on really big networks. Gephi is this. It's been called it's a generalized open source network visualization tool. It will read files, so you can import different sorts of databases, including PAYAC network files or other types of edge lists. Its standard format is an edge list, if I remember right. Is that right, John?
Yeah.
Yeah.
You have a node in edge list, and you get it through the laboratory. Go to the, and then.
Yeah. So this is just a silly little example about people who have different kinds of chef jobs. It has no meaning for us in the health world. The things of the different types of layouts that it's again a Windows tool, so you have all these different types of layouts that you might use. All of these layouts are different versions of the Spring embedders. So the Force Atlas, the Force Atlas 2, the way they differ tends to be about how they deal with either weighting edge crossings or node overlaps, right? So the Fruchterman Rheingold one here, you can run it for as long as you want, and then you can see it sort of reach some kind of equilibrium because it's not changing anymore. So I'm going to stop it. And then this is something you got to kind of get used to. Is in PAYAC, your visualization is what it is. Here, this is just a scratch space rendering, and to see what the network really looks like, you need to go over to the preview set and then refresh that preview, and this is the way the network works. All right. And so this is that classic curvy edge style that PAYAC Gephi is famous for. You can turn it off, and I remember where it is now. It's over here on the edge. Yeah. So you can turn that off, refresh, and then it goes back to what we would expect. All right. Again, this is a program that the nice thing about this program is that it's free, it's open source, it works on a Mac, right? And so those things make it really nice for people who want to work on Macs and are broke. So that's the advantage of it. It also has a bunch of different plugins, and just like you can load packages in R, you can load all these different packages that work with Gephi to do different unique kinds of layouts, including the ability to write out those searchable interactive graphics I was telling you about. John?
Which is cool. Unfortunately, it's free, so version control is with the plugin. So there's a there's a Gephi community. If you want to use this tool, really get hooked up on the Gephi community. That'll save you a lot of pain and misery. And the other thing I'd say is it's a little weak on network measures. I mean, you can get sort of basic degree and things like that, but even you can calculate a modularity score, but even clustering is something that this program doesn't support particularly well.
One of the nice things that it has, though, are built-in color ramps. So, for example, I can do something like take my nodes, and I want to change their color, and I'm going to do it based on some attribute. I could take it, say, on in degree, and I can figure out what colors I want. I can change the colors. I can apply it to that. I might do the same thing with size, The attribute now might be, say, in degree. Apply that. So now I get nodes that are bigger or smaller, and I have a different color ramp. Go over to the preview, refresh, and you get that nice scaling quickly. So it has the ability to do those kinds of things quite nicely. And so you can see the person who has their, and this is not a person, this is a state in a life course. So this person's their first restaurant job. Everybody in this population had a first restaurant job. Some went on to own their own establishment, for example. And so you can think about these kinds of things. It really has some nice features. And then you can essentially just export it to PDF or SVG or what other sort of editing software you like to work in. John?
One quick question. So what editing software, it sounds like you use Adobe Illustrator?
No, I use Illustrator almost entirely. And the advantage of Illustrator is that it's got very high-end graphic features for things like transparency, coloring, line thickness, fonts, these types of things. The disadvantage is it's expensive. It's free for me. It's not free for me. Duke buys it for me, and so that works out fine. If you're not so lucky, then you might want to use a different editing. There are some free SVG and PDF and EPS editors. I've not played with them. Jake?
I was going to suggest the open source equivalent is called GIMP, which is fine.
Okay.
I'm good.
Question in the back there?
Yeah, I noticed people don't really use keys that much. The graph are so complicated, people don't try to use keys. Keys are falling on the favor, or
You mean keys in terms of the? Yeah. Yeah, that's a mistake. They should have. You should always have a key. If you're printing a network, you should have a key. The problem is none of the software programs really produce one for them automatically, and so you typically have to draw one yourself. And that's kind of a pain in the neck, and people are in a hurry, so they just go straight to the outset from it. All right, let's take a quick break.